Everyone.
Hi. Before we get started, special announcement concerns everybody. I made a mistake. When I set up our grade book, I transposed 2 of the weights. So the grade book should have 50% weight on the test and 15 on the semester exam. I transposed those in the grade book. I fixed that on Monday morning. So if you saw a surprising change in your score, that's what it would have been related to. For the most part, like the class average moved like a percentage or something. So it wasn't like, I don't think it was traumatic for anybody, but I just wanted to put that out there that did happen. And if you saw some score change, like what happened to my grade? It moved. I don't understand what happened. That's what it would have been. Okay? Yeah, Hannah.
It's at 1:30.
Sounds good. So, again, some of us might have gone up, some of us might have gone down, depending on how where your scores were at. Like if you had if you have some missing homeworks, and now you good test scores, like your grade probably went up. If you had all your homework in and kind of so-so test scores, your grade probably went down a little bit. Just kind of depends. Okay. Today, what I want to start with is I got a couple of emails from people about Chapter 14 Delta Math, particularly the last problem type, and there being some issues with that. I want to run through an example or two doing that. And then we'll get on to the stuff we're doing today, okay?
I know that one. I don't want to see you turn that.
Okay. So this was the section that I got questions about. So I'm just going to kind of run through an example or two to make sure we feel okay about what we're doing. If you had trouble completing things. So we want to start by capturing all the information we know about the key features. So we'll start by factoring. I notice that I can factor the numerator here. So that'll reduce down to just 4. Because we're able to reduce, we have a whole or removable discontinuity. So I set the piece that I reduced out equal to 0. That's the x coordinate. And then I plug back in. There's nowhere to put the x, it's just a constant function, so the y coordinate is 4. So there's my whole. I have no vertical asymptote, right? This is not a rational function anymore, right? So I have no horizontal asymptote either. And x-intercept, there's no x to solve for there, so it has no x-intercept. We do have a y-intercept though. Right, if I plug 0 in, I get 4. So 0, 4 is my y-intercept. So that's all I need to record. So I'll start my whole. I'm going to be careful because it's a little bit touchy, but I notice that like when I get close to one of these lattice points, it kind of like sucks in there and locks. Now I got a y-intercept there at 0, 4. And that's it. Those are the only 2 key features. We'll just plot and hit submit. Notice that if I didn't use them, I don't need to do anything. Alex?
Can you just explain why like there was no vertical asymptote or horizontal?
If I look at what it reduced down to. Is there a denominator? Okay, can't have a vertical asymptote then. Is it a rational function? 4?
Oh, no.
No, so it doesn't have a horizontal asymptote. So it's because it reduced down to not a rational function. I don't get those features. Is that okay? Let's do one more and then move on to today's stuff. Sound good? Okay, so I want to start by factoring numerator and denominator. The numerator should be easy. X squared minus 16 factors 2.
X plus 4, x minus 4.
Okay. The denominator is a little bit of a hassle. Why is that?
Because you can't do the quick trick to factor it in 3 terms.
Well, it's because the leading coefficient is a 1, right? So we need to find the two numbers that multiply to give us -2 times -20, and then add to give us 13. What are those two numbers? 5 and 8. Unfortunately, that doesn't take us straight to the factored form. We have to do this factor by grouping stuff. From the first group, I can take out a -2x. From the second group, I can take out a 5. Both of them have an x minus 4 in common, and then the leftovers would be -2x plus 5. Is everybody okay with the factoring I did there? Again, it should be an expectation that you're still able to do that greatest common factor not equal to 1 factoring relatively quickly and accurately. That was a mastery skill in Algebra 2. The expectation is that you still kind of hang on to that. Okay, I can go ahead and reduce now. So because I was able to reduce the x minus 4 fully from the function, I do have a whole or removable discontinuity. The x value is 4, and the y value is going to be f of 4. So when I plug that in, I get 4 plus 4 over -2 times 4 plus 5. So that's going to be 8 over Q. Yes, -3. So we have 4 comma -8 thirds. It's supposed to be a 3 down there. Yuck, but okay. Next, I'll do our vertical asymptote. So I'll take the denominator, set that equal to 0. So when I do that, I get 5 over 2, or I'll think about it as like 2.5. Oh, that, no. And it's a vertical asymptote, not a x-intercept there, dum-dums. Sorry, guys. I'll do my horizontal asymptote. If I look at my reduced, I have a degree 1 over a degree 1. That tells me I have a horizontal asymptote with the equation y equals leading coefficient in the numerator over leading coefficient in the denominator. The leading coefficient in the numerator is
1.
The leading coefficient in the denominator is
-2.
So I should have y equals -1/2. So far, so good. For my x-intercept, I just take the numerator, set it equal to 0. For my y-intercept, I plug 0 in for x. That's going to be 4 over 5. And that's all my features that I need for this problem. Everybody's okay? Now I ripped through some of those, and this is kind of the lousy part, is you have to be a little bit careful in placing these things. So vertical asymptote is at 2.5. So that's, trying to get it right in there. Yeah. Try the mouse pad. There we go. So there's 2.5. I guess maybe not really. We'll see what it says. Maybe it'll bark at me. We'll see if we have to adjust once we draw the graph. Horizontal asymptote at -0.5. X-intercept at -4.0. Y-intercept at 0.4. And we got a hole at 4, -8/3. So -8/3 is like -2 2/3. Nope, that's too high. Let's hit plot. Now it's passing through all my points, right? It's following all my asymptotes. So I think this should be good. That's going to be my final check to see, like, all these things are like decimals, so I have to be a little bit careful where I'm placing them. But as long as I feel like I'm close and I do the plot, it catches them, which it looks like it does. I think I should be okay. Hit submit, and it took it. So you just have to make sure when you hit the plot, that everything is going through what it's supposed to. And if it's not, then something's not quite in the right place, and you might have to make a little adjustment. But does that feel okay doing this? Again, you have to play with a little bit, but it's nice in that, like, you get a feel for what these graphs are going to look like, right? Okay. Today, we're going to take a little bit of a diversion, and we're going to talk about multiplying, dividing, adding, and subtracting rational functions before we get to solving. That's 14.2 is solving. But if we can't, do this simplification, the solving becomes really a big problem. So I want to make sure we go through how to do this and take a little day to work on these sub-skills. Essentially, the process for multiplying, dividing, adding, and subtracting rational functions is the same process as adding, subtracting, multiplying, dividing fractions, with like the minor caveats that instead of dealing with numbers like you are with a fraction, you're dealing with a polynomial, right? A fraction is an integer over an integer. A rational function is a polynomial over a polynomial. The steps are the same, it's just like how you execute the steps that's a little bit different. So we're going to look at an example of each of these. Add, subtract, multiply, divide. We're going to start with the fraction. Do the fraction example, build out the process, and then we'll generalize that to the polynomial. Everybody okay? All right. So if I have a problem like 4/5 times 35 over 12, what I want to do is I want to start by doing a prime factorization of all of the numbers in my fraction. So prime factorization of 4, 5, 35, and 12. Do you guys know what a prime number is? You remember this? What is it? What's the definition? N1, right? Yep, that's wonderful. So prime factorization is breaking that number up into a product of primes. Okay? So what is the prime factorization for 4?
2.
Not 2 and 1, because 2 times 1 isn't 4. But 4 isn't prime. 2 times 2. What's the prime factorization for 5? It's just 5, right? It's already, we don't have to include the 1s. 1 isn't a prime number, by definition. 2 is the smallest prime number. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37. You guys don't know all these by heart? Come on, guys. All right, 35.
7, 7.
Okay, I'm going to write as 5 times 7 if that's okay with you. I usually like to go small to big. And then 12.
3, 2, and 2.
3 times 2 times 2. I'm going to write the 2's first, though. Again, it doesn't really matter. It's multiplication, it's commutative. The order that you write them doesn't matter. I just like to write small to big, or else I lose track of them. Okay. So I'm going to now rewrite this as the prime factorization. Is everybody okay with what I did? Just did my prime factorization. Sometimes, like drawing the factor trees, if you're down with that, you remember doing factor trees back in like elementary or middle school? You can do that if you're more comfortable doing that. I think for the most part, these are numbers that are small enough you can do that. Okay, so I did my prime factorization. Now I'm going to reduce. Anything on a top level of my fraction can reduce with anything on a bottom level of my fraction. So like this 2 can reduce with that 2. They become 1. Those 2's can reduce. These 5's can reduce. And then we just multiply across. So in the top, I have 1 times 1 times 1 times 7. On the bottom, I have 1 times 1 times 1 times 3. 7/3 is my answer. Are you okay? Remember doing this back in like elementary or middle school or both? Probably both, right? Get into fractions by like 5th grade or something, I think, right? Okay. So if we're doing this now with a rational function, the only step that's different is the prime factorization step, right? We're still doing a prime factorization, but because we're dealing with polynomials instead of integers, the process to factor a polynomial is different than that to factor an integer. So what does a prime polynomial mean? For a prime factorization of a polynomial, it just means the factor completed, right? Like doing the same factoring we've been doing in chapter 13. Okay? Nothing new. Same stuff. So, x squared plus 5x plus 6, how does that factor?
X plus 5x plus 6, right?
X plus 3 and x plus 2. Now, I know this is a prime factorization because x plus 3, I can't factor that anymore. And x plus 2, I can't factor that anymore. So that is a prime factorization because the factors x plus 3 is prime. Not because 3 is a prime number, but because I can't factor the polynomial x plus 3 anymore. Right? All right, x squared minus 4.
X plus 7 is minus 2.
Okay. Oops, that's a 2. And then x squared minus 5x plus 6. X minus 3, x minus 2. And then x squared minus 9.
X plus 3.
Yeah, x plus 3, x minus 3. Okay? Everybody happy with the prime factorization here?
Couldn't you also do x minus 6x plus 1?
That would multiply to give you negative 6, not positive 6. Though. It does add to give you negative 5, though. Everybody happy? Prime factorization complete, right? No different than what we've been doing, right? Not a big deal. Now let's reduce. Anything from the top can reduce with anything from the bottom. So let's see, I got x plus 3's that can reduce, x plus 2's can reduce, x minus 2's can reduce, x minus 3's can reduce. What am I left with?
1.
Done. You guys remember doing this last year? Right, you did this in Algebra 2-ish. Doesn't hurt to review it, but the expectation is that you still kind of remember doing this. Yeah. Division. If I divide two fractions, the first step is going to be rewrite this as a multiplication problem, right?
First of the second.
Yeah, I remember in elementary school I learned dividing fractions as easy as pi, flip the right, and multiply. Rhymes. But that's the first step. After we've rewritten this as a multiplication problem, then it's the same thing as before, right?
Yep.
Okay. So, my first step. Multiply by the reciprocal. And then prime factorization, reduce, and multiply across. What's the prime factorization of 36? 5 and 6 is 30, and 6 is in prime.
No.
3's 3322.
3322, yeah. Right, 36 is 6 times 6, and 6 is 2 times 3, right? Since you have two 6's, you have two 2 times 3's. Again, the order you write that doesn't matter. I like to go small to big when I do mine. Prime factorization of 35. 5 times 7, it's like we did that before. Prime factorization of 12.
2, 3.
Yeah, we did that before, right? 2, 2, 3. And prime factorization of 25.
5 times 5.
5 times 5. Okay, let's reduce. What are we left with on top? 3 times 5. What are we left on the bottom? And we're done, right? Easy peasy, mental math, love it, right? What we don't want to do is multiply 36 and 25 and then 35 and 12 and then have to factor those numbers to reduce, because that's going to be a nightmare, right? The bigger the number is, the harder it is to factor. We don't want to do that. We want to reduce and then multiply, especially when we're dealing with polynomials, right? Because you've seen how much more difficult it is to factor like a degree 4 polynomial than it is a degree 2 polynomial, right? Like you don't want any part of that. All right, let's do a division problem with a rational function. Again, first step is to change the division into multiplication. How do I do that? Yeah, we multiply by the reciprocal, right? So the first fraction just stays the exact same. And the second one, flip-a-roosies. Then we'll factor. How do I factor x squared minus 3x minus 4? X minus 4, x plus 1. How do I factor x squared minus 2x?
Take out an x.
Take out an x, right? There's just a greatest common factor there. That's all we can do. And then how do I factor x? It's done, right? It's prime already. How do I factor x plus 1?
Prime already.
I can't, it's prime already, so that's nice. And then we reduce. Oops. And we're left with just x minus 4 over x minus 2. What do you guys think? It's all right? Okay. Multiplying and dividing, easy. Adding and subtracting is the harder part, right? Because when we add or subtract fractions, what do we have to have? Common denominator. Now, when you add or subtract like fractions, any common denominator is usually fine. It's like marginally just a little bit more work if you don't choose the least common denominator. When dealing with rational functions, if you do not use the least common denominator, you make yourself a nightmare. So it's going to be really important that we're able to find the least common denominator. So we're going to emphasize that with the numeric problem and talk about how to do that and the real process for that, because a lot of times we skate through this in elementary school and don't do a very good job of emphasizing really what's going on here. So let's say we want to add 7/12 plus 11 over 20. Yes, sir.
Multiply the right side by 3 and then multiply the left side by. Oh, wait, no. Skipping out.
So first things we want to do is we want to do a prime factorization, but really specifically only for the denominators. That's the only part I care about. So the prime factorization of 12 is 2 times 2 times 3. And the prime factorization of 20 is 2 times 2 times 5. Okay. Step 2 says multiply the top and bottom of each fraction to make the least common multiple in each denominator. So, what is the least common multiple of 12 and 20?
60.
Great. How'd you get 60, Mark?
You just keep adding until you find where 12 and 20 meet up.
Okay. How are you going to do that with polynomials? That's fine, but how are we going to do that with polynomials? That's a nightmare now, right?
Yeah.
Okay. So let's talk about like the more precise definition. What you described was not wrong, right? But it's not going to work for polynomials. So the precise, the rigorous definition of what's going on, my least common multiple should contain every distinct prime from 12 and every distinct prime from 20. If I look at 12, I have 2 distinct primes, 2 and 3. If I look at 20, I have 2 distinct primes, 2 and 5. So my least common multiple I know is going to have a 2, a 3, and a 5 in it. And then I'm going to look at the powers of each of those. So in 12, I really have 2 squared times 3. And in 20, I have like 2 squared times 5. My biggest power on 2 is 2. My biggest power of 3 is
1.
My biggest power of 5 is 1. That's how I'm going to build my least common multiples. Okay? Each distinct prime to the biggest power of that prime. Everybody's okay? So, what do we need to multiply this first fraction by to make the denominator be 2 squared times 3 times 5? I have the 2 squared, I have the 3, I don't have the 5. How about the second fraction?
We got 3 on.
I need the 3. Everybody's okay? Step 3 says multiply the numerators and add them. Numerators only. The denominator here is going to be 2 squared times 3 times 5. I'm not going to multiply it out because I want it in a factored form, because the last step is to check to see if I can reduce. What do I have to do to reduce? I need the factored form, right? I want to hang on to that factored form until I'm sure I've done absolutely everything I can do before I lose that, because if I have to go back and do something else, I'm just going to refactor it. No, I don't want to do that again. All right, 7 times 5 is 35. 11 times 3 is 33. 35 plus 33 is 68. If I do the prime factorization of that, that's 2 squared times 17. So I end up with 17 over 15. Is that okay with what we did there? Okay. Let's do the same thing now for rational function. Yeah? Okay. So I want to start by factoring completely, specifically the denominators, but oftentimes it's a decent idea to check the numerator in case there's any reducing you can do in either one of the fractions. If you can do that, you should. It's rare. It's probably a poorly designed problem, but let's do that. Obviously, x minus 3, that's prime. Nothing to do there, right? X squared plus 4x plus 4. How does that factor?
X plus 2, X plus 2.
X plus 2 times x plus 2. I'm going to write that as x plus 2 squared, because it'll make it easier when I build my least common multiple here in a moment to write it that way. Is everybody okay? All right. X is prime. And then x squared plus 7x plus 10.
X plus 5, X plus 2.
X plus 5 and x plus 2. If this was x plus 5 up here, could I reduce? No! Why not?
Because you're not multiplying them. You're
Yes, it's
adding.
an addition symbol. I can only multiply. I can only reduce diagonally across multiplication.
That scared me.
Good. I want to get everybody's attention because that's a super common mistake, right? I want everybody to hear that. All right. Let's make our least common multiple here. How many distinct primes do you see in the denominators?
2.
2. They are
X plus 5, X plus 2.
x plus 5 and x plus 2. What's the biggest power of x plus 5 I have?
1.
To the first. Good. The biggest power of x plus 2 I have?
Squared.
Squared, or to the second. Okay. What do I need to multiply this first fraction by to get that least common denominator? I have the x plus 2 squared,
Plus 5.
but I'm missing the x plus 5. What do we have to multiply the second second fraction by?
X plus 2.
I need another x plus 2, right? I have an x plus 5, and I have one x plus 2, but I need a second one. Is everybody happy? You feel comfortable on how I made the least common denominator here? Okay. I'm going to multiply the numerators out. Is it okay if I FOIL this stuff out in my head? Everybody okay? I'm going to combine my like terms now. So x squared plus x squared is 2x squared. 2x plus 2x is 4x. And then I have minus 15. And then I'm going to check here for just a moment to see if I can reduce. To be able to reduce this, I need to see if I can factor the numerator. So I need two numbers that would multiply to give me negative 30, but then add to give me 4. So 1 and negative 30, do those add to give me 4? No. How about negative 1 and positive 30? Okay, how about 2 and negative 15? Negative 2 and positive 15. Negative 5 and 6. 5 and negative 6. Those are all the factors that give us negative 30. Did it work? I forgot 3 and 10. Right? That doesn't work either though, right? Okay. So we're done. No reducing to do. Notice that I didn't bother multiplying the denominator out. Don't do that. Like, what a hassle to multiply that out. Like, bleh, leave it in the factored form. Notice the numerator is technically in factored form. Like, we checked to see if we could factor it, and we can't. So it's done. We're going to leave our answers in factored form here. Mostly because it's just easier. But it's okay. It's not wrong to multiply it out, but like, oh goodness, you guys got better things to do than to multiply that stupid stuff out, right? All right. Subtraction. Anything meaningfully different when we deal with fractions, if we're adding versus subtracting? No. How about for rational functions? Not really, but there is a place where, like, I'm going to show you this, where the most common mistake is made. And come test time, still at least half of you are still going to make this mistake even after I show it to you and remind you 3 times that, like, hey, make sure you do this. So let's look at where that happens. So I have another example here, a subtraction example, just so I can show you where the most common mistake in dealing with this is made, so that come test time, maybe a few more of you that would make the mistake would fail to make that mistake. All right, so we start by doing a prime factorization. How do I factor 2x cubed minus 4x squared?
I would take a 2x squared.
Okay, I can take out a 2x squared. What am I left with? X minus 2, right? And then x plus 1 is prime. Obviously 3 was prime. I wrote it without saying it, but I checked. How about x to the 4th minus 2x cubed?
X cubed.
X cubed. Oops. I'm going to do this. Leave myself a space here. Do that. Okay. All right. Let's make our least common multiple. How many distinct prime factors do you guys see?
No, 3. Oh, not 2.
What are the, there are 3. What are the 3?
2x squared, x cubed, and x minus 2.
No.
X plus 1.
Nope. We're only looking at the denominators.
Or was it the x minus 2 and the unfactored ones?
Nope. There's 2. There's x. And then there's x minus 2. Those are your 3 distinct prime factors. Super common for students to struggle recognizing that x squared and x to the cubed are just powers of the prime x. That's part of the reason why I chose this example, to like, oh yeah, okay, I see it now. All right, the biggest power of 2 is?
1.
To the 1st. The biggest power of x is? To the 3rd. The biggest power of x minus 2 is? To the 1st. That's our least common multiple. What do I need to multiply the second fraction by to get that least common multiple in the denominator?
2. X cubed.
Nope,
X.
just x, right? I have the 2, I have the x minus 2, but I only have x squared here. I need x to the 3rd, so I need to multiply in by 1 more x to get it to x to the 3rd, right? Everybody see it? What about the second fraction? What do I need to multiply that one by to make the least common multiple in the denominator?
2.
Just a 2. Everybody okay here? All right. So multiply the numerators out, keep the common denominator. Now I made this the most common mistake that'll be made. Oops. Sorry. This should be. I made the most common mistake that'll possibly be made in this chapter. Take a look and see if you can see it. I did it intentionally.
You didn't multiply it, so the x plus or x minus 2. So,
What do you mean?
like,
Oh, the numerator and the factor.
oh,
What is the mistake? Ian.
You're not supposed to leave the 2x plus 2 should have been 2x minus 2.
Yes. This is the mistake. This should be minus. The reason is
oh, you're right.
the negative has to distribute through as well, right? That's the place where probably 2/3 of you are going to make the mistake on the test, is remembering on these subtraction problems, we make our least common denominator, you got to distribute the minus through. What do we do with the minus? Gotta distribute the minus through. I'm gonna say it one more time, because in my experience, it takes about 3 times for everybody in the class to hear it. Because, we got Sean on his computer and Krista maybe awake or not, and all kinds of people doing whatever. I'm gonna say it one more time. What do we have to do with the minus? Distribute it through, okay? I'm gonna hope that as many as possible have absorbed that. Now, can we remember it a week from now? I don't know, but better chances after I say it 3 times and make a big ordeal out of it, right? All right, so, still not done. What do I still need to do?
Reduce if possible.
Yeah, combine my like terms. So 3x minus 2x is x, and then I have a minus 2 on top. And then I need to check to see if I can reduce. We sure as heck can, right? What are we left with? 1 over 2x cubed. Remember, when we reduce, they become 1s. Very common for students to just write that as 2x cubed. Very wrong to do that. Remember, if it's in the denominator before reducing, it better be in the denominator after reducing. And if you don't have a numerator left, then the 1's got to go up there. Does everybody feel okay with what we did today? Should be review from Algebra 2, right? You did this all then. I need to review it because we're going to talk about solving first with equations and then inequalities. We got to be able to deal with it adding and subtracting, multiplying, dividing, we got to be able to find those least common multiples, and I want to review this before we move forward. I'm going to stop here for today. I'm going to hand you guys this handout. This is going to be your homework for this lesson. So just take one and pass it back. Frankie, you gotta pick some stuff up. There's sheets in the back for you. I'm gonna give you guys an extra one. Think about how this left for. Yes, go ahead. On here where it's asking you to find the least common multiple, for the first page where we're asking for least common multiples, please kind of do it the same we did before, where you write the prime factorization for each and then you write the least common multiple. Right? Because it doesn't do us any good if we can't find the least common multiple the right way, where you can scale it to the polynomial situation.
Or turn on OneNote, or no?
Yeah, this will be turned into OneNote still. Yep. But I feel like for these handouts where I ask you to do that, where it's not the review, I like to give it to you in hand as well, so you have something to, at least to look at if you're gonna do it on a separate sheet of paper and load it in, or you just do it on this sheet. It doesn't really matter to me. You guys have 40-something minutes or 35-something minutes left in class to work on this thing. I think if you're focused, you could probably bang this whole thing out in before you have to go. I don't think that's unreasonable, particularly since you've done this before. I would suggest, let's hammer these concepts home and lock them in and get some good practice in right now and reduce what you have to do outside of class time. That would be what I would do. But my main goal as a high school student was I didn't have to take anything home. Good day was when everything could stay at school because all the work was done before I had to go home. But that was me, Yeah, any questions? You guys feel good? What haven't we done yet this chapter?
Homework quiz.
Homework quiz. What might be a good thing to expect here coming up this week?
Homework quiz.
Homework quiz. How many more class days do we have this week? 1. If it's going to happen this week, when do you think it's going to happen? Yeah. What do you think it's going to be on? Key features. Finding key features for rational functions. So the 14.1 lesson. Okay?
What is it?
The 14.1 lesson. Finding the key features. Right? Like you did we did 3 days on it between the 2 days of lesson and then the delta math.
Oh, yeah.
right? Like basically did 3 days on that topic, so we should feel okay about that. Where you can find the domain or the vertical asymptote or horizontal asymptote or x-intercept or y-intercept or whatever. So I'll just ask you to, here's a function, find this or that key feature for it. Here's another one, find this or that key feature. So you should be able to find key features, and I'll, keep changing the function so that it's not like if you did the factoring wrong on one of them, everything's gonna be wrong because you did the factoring wrong. You'll have like more than one opportunity to factor something correctly. Everybody feel okay? Got the plan? Okay, I'm gonna shut my trap and let you guys get to work.